Sym Mo was created to supplement the learning of symmetry and molecular orbital theory, which is taught in CM 1111, 2101, and 3231. Let's have a look at how it works. Sym Mo presents the symmetry and molecular orbital information for 8 molecules. The 8 molecules are chosen as they cover the various point groups. This app was developed by the Department of Chemistry and the School of Computing at the National University of Singapore. From the top bar, we can choose one of the 8 molecules, so let's choose water. To work out the symmetry present in the water molecule, we can have a look at the bottom bar. C is the rotation axis, sigma is the reflection plane, and I is the inversion point. There is a C2 rotation axis in water because if we rotate around this axis, which is rotation of 180 degrees, which is 360 divided by 2, the same molecule is obtained. There are 2 vertical reflection planes, also called the sigma V planes. If we reflect through this plane, we will get the same molecule. Likewise, if we reflect through the other vertical plane, we would also get the same molecule. There is no inversion point in water, and hence the option is unavailable. If we go back to the Lewis dot and cross diagram page and touch anywhere, the point group flow chart appears. From the symmetry present in the water molecule, which is 1 C2 rotation axis and 2 sigma V planes, the point group can be determined as C2V. Now let us look at the molecular orbital information. Here we have the MO diagram, the bond order, and the molecular electronic configuration. There is an audio recording that explains how the MO is constructed.
Water is assigned the point group C2V. The order of principal rotation axis is 2, which is calculated by taking 360 degrees divided by the smallest angle to rotate to obtain an identical molecule. In this case, the smallest
Only atomic orbitals of the same symmetry can combine to give molecular orbitals of that symmetry. Hence, we need to assign the symmetry labels of the atomic orbitals, and for this we use a character table.
Click on the text icon to view the character table. The first row has the symmetry elements of the molecule, which indicate the symmetry operations to be performed. The first column has the symmetry labels of orbitals. Let's look at how to assign the symmetry labels to the oxygen AOs.
The atomic orbitals of the same symmetry are then combined to give you molecular orbitals of that symmetry. Each individual atomic orbitals to molecular orbitals combination is shown, arranged from the lowest energy at the bottom of the drop-down menu to the highest energy at the top of the drop-down menu. Let's choose 1b2 bonding molecular orbital. This is formed by addition of the atomic orbitals to give molecular orbitals, and if we touch the swipe bar, we can see from atomic orbitals we can add together to give you the molecular orbitals. We can also choose its corresponding 2b2 anti-bonding molecular orbital. Here, if we touch the side menu, is combined by subtraction to get to the molecular orbital. For other more complex molecules like methane, if we go back to the drop-down menu, choose methane. Rotating within the app allows us to see the symmetry much clearer, which is not possible in a textbook. If we rotate around this axis, it's easier to see. Likewise for reflection, if we choose a more difficult plane, right, we can see the reflection through that plane. If we use the MO diagram tab, we can also see the molecular orbitals of methane. So these are the atomic orbitals, and if we add the atomic orbitals, we can form the molecular orbitals. So from atomic orbitals to molecular orbitals here. So that's basically the app. Please download and use it. It's available on the iPad, iPhone, and Android. Thanks.